The magic of numbers. Number patterns. Yes. The study of the mathematics begins with numbers. In school, after we learn how to count and represent numbers using words or digits or physical objects, we spend many years manipulating numbers through addition, subtraction, multiplication, division, and other arithmetical procedures. And yet, we often don't get to see that numbers possesses a magic of their own, capable of entertaining us if we just look below the surface. Really? Let's start with a problem given to a mathematician named Carl Friedrich Gauss. Yes, Gauss. When he was just a boy, Gauss's teachers asked him and his classmates to add up all the numbers from 1 to 100, and a tedious task designed to keep the students busy while the teacher did other work. Gauss astonished his teacher and classmates by immediately writing down their answer, 5050. How did he do it? Gauss imagined the numbers 1 through 100 split into two rows, with the numbers 1 through 50 on the top and the numbers 51 through 100 written backward on the bottom, as shown below. Yes. Gauss observed that each of the 50 columns would add up to the same sum, 101, 101, and so their total would just be 50 times 101, which is 50, 50, so 5050. Yes. Look at the diagram. Splitting the numbers from 1 to 100 into two rows. Each pair of numbers adds to 101. Sure. Gauss went on to become the greatest mathematician of the 19th century, not because he was quick at doing mental calculations, but because of his ability to make numbers dance. But because of his ability to make numbers dance. In this chapter, we will explore many interesting number patterns and start to see how numbers dance. Some of these patterns can be applied to do mental calculations more quickly, and some are just beautiful for their own sake. We've used Gauss's logic to sum the first 100 numbers, but what if we wanted to sum 17 or 1000 or 1 million? We will, in fact, use his logic to sum the first n numbers, where n can be any number you want. Sure. Some people find numbers to be less abstract when they can visualize them. Sure. We call the numbers 1, 3, 6, 10, and 15 triangular numbers, since we can create triangles like the ones below using those quantities of dots. You might dispute that one dot forms a triangle, but nevertheless one is considered triangular. The official definition is that nth triangular number is 1 plus 2 plus 3 plus ... plus n. Sure, please look at the diagram. The first 5 triangular numbers are 1, 3, 6, 10, and 15. Notice what happens when we put two triangles side by side as depicted on the opposite page. Sure. How many dots are in the rectangle? Wow. How many? It's each 1, 2, 3, 4, 5. 25 dots are there. No, 5 to 30 dots are there. Since the two triangles form a rectangle with 5 rows and 6 columns, there are 30 dots altogether. Hence, each original triangle must have half as many dots, namely 15. Sure. Of course, we knew that already, but the same argument shows that if you take two triangles with n rows and put them together as we did, then you form a rectangle with n rows and n plus 1 columns, which has n times bracket n parenthesis n plus 1. So parenthesis n plus 1 times n. Sure. Dots, often written more succinctly as a parenthesis n plus 1 times n dots. As a result, we have divided the promised formula. We have derived the promised formula for the sum of first n numbers. Sure. please look at the formula. 1 plus 2 plus 3 plus plus n equal parenthesis, open parenthesis, n plus 1 close parenthesis times n divided by 2. Yeah, because 2 is because you just doubled when you flip it over, flip it. Notice what we just did. We saw a pattern to sum the first 100 numbers and were able to extend it to handle any problems of the same form. If we needed to add the numbers 1 through 1 million, we could do it in just 2 steps. Multiply 1 million by 1,000,001, then divide by 2. Yes. Once you figure out one mathematical formula, other formulas often present themselves. Sure, this is like a mushroom. If you find one mushroom, you could most of the time find any other mushrooms around the mushroom. For example, if we double both sides of the last equation, we get a formula for the sum of first n even numbers. Please look at the formula. 2 plus 4 plus 6 plus in 2n equal open parenthesis n plus 1 close parenthesis times 2 times n. What about the sum of the first n odd numbers? Let's look at what the numbers seems to be telling us. Sure. What is the sum of the first n odd numbers? Sure, of course. What is the sum of the first n odd numbers? 1 equal 1, 1 plus 3 equal 4, 1 plus 3 plus 5 equal 9, 1 plus 3 plus 5 plus 7 equal 16, 1 plus 3 plus 5 plus 7 plus 9 equal 25, The numbers on the right are perfect squares. 1 times 1, 2 times 2, 3 times 3, and so on. It's hard to resist noticing the pattern that the sum of the first n odd numbers seems to be n times n, often written as a n square. Sure, but how can we be sure that this is not just some temporary coincidence? We will see a few ways to derive this formula in chapter 6, but such a simple pattern should have a simple explanation. My favorite justification uses a count the dots strategy again and remind us of why we call numbers like 25 perfect squares. Why should the first 5 odd numbers add to 5 square? Just look at the picture of the 5 by 5 square below. Sure. How many dots are in the square? That's 25, right? This square has 5 times 5 equal 25 dots, but let's count the dots another way. Start with the 1 dot in the upper left corner. It is surrounded by the 3 dots, then 5 dots, then 7 dots, then 9 dots. Consequently, 1 plus 3 plus 5 plus 7 plus 9 equal 5 square. Wow. If we started with an n by n square, then we can break it into n backward L-shaped regions of the sizes 1, 3, 5, open parenthesis 2n minus 1 close parenthesis. When viewed this way, we have a formula for the sum of the first n odd numbers. 1 plus 3 plus 5 plus open parenthesis 2n minus 1 close parenthesis equal n square. Wow. Aside. Later in this book, we will see how the approach of the counting dots and the general approach of the answering the question in two different ways leads to some interesting result in advanced mathematics, but it can also be useful for understanding elementary mathematics as well. For example, why does 3 times 5 equal 5 times 3? I am sure you haven't even questioned that statement since you were told as a child that the order of multiplication doesn't matter. Sure, mathematicians say that multiplication of numbers is commutative. Wow, didn't know that. But why should three bags of 5 marbles contain the same amount as 5 bags of 3 marbles? The explanation is simple. If you just count the dots in a 3 by 5 rectangle, counting row by row, we see 3 rows of 5 dots a piece, giving us 3 times 5 dots. On the other hand, we also have 5 columns with 3 dots a piece, so there are also 5 times 3 dots. Let's go back. Okay, let's get back to our topic. Let's apply the pattern from the sum of odd numbers to find an even more beautiful pattern. Wow. If our goal is to make the numbers dance, then you might say we are about to do some square dancing. Yes, square dancing. Consider this interesting pyramid of the equations. 1 plus 2 equals 3. 4 times 5 times 6 equals 7 plus 8. As you add the next number, as a consequence, this piles of the formula becomes pyramid, right? 9 plus 10 times 11 plus 12 equals 13 plus 14 plus 15. 16 plus 17 plus 18 plus 19 plus 20 equals 21 plus 22 plus 23 plus 24. Really? Didn't know that? And always on the left hand side is one term more in order to balance the both sides. Wow. 25 plus 26 plus 27 plus 28 plus 29 plus 30 equal, which was 6 terms, 31 plus 32 plus 33 plus 34 plus 36, 35, which is 5 terms. So left hand side is one more term. Yeah. What patterns do you see? It's easy to count the numbers in each row, 3, 5, 7, 9, 11, and so on. Next comes an unexpected pattern. Sure. What is the first number of each row? Judging from the first 5 rows, 1, 4, 9, 16, 25, they appear to be the perfect squares. Why is that? Let's look at the 5th row. How many numbers appear before row 5? If we count the numbers in the preceding 4 rows, we have a 3 plus 5 plus 7 plus 9. To get leading number of row 5, we just add 1 to this sum, so we really have the sum of the first 5 odd numbers, which we now know to be 5 square. Wow. Now let's verify the 5th equation without actually adding any numbers. What would Gauss do? If we temporarily ignore the 25 at the beginning of the row, then there are 5 remaining numbers on the left, which are each 5 less than their corresponding numbers on the right. Sure. Wow. Comparing Please look at the diagram. Comparing the left side of the row 5 with the right side of the row 5. Sure. So 25 is the same. So 26 minus 31 equal minus 5. 27 minus 32 minus 5. 28 minus 33 minus 5. 29 minus 34 minus 5. 30 minus 35 minus 5. So it's remained 5 minus 5, right? Hence, the 5 numbers on the right have a total that is 25 greater than their corresponding numbers on the left. But this is compensated for by the number 25 on the left. Hence, the sum balances as promised. Wow. By the same logic and a little bit of algebra, it can be shown that this pattern will continue indefinitely. Wow. Phew. Aside. For those who wish to see the little bit of algebra now, here it is. Row n is preceded by the 3 plus 5 plus 7 plus plus open parentheses 2n minus 1 close parentheses. Sure. Row n is preceded by the 3 plus 5 plus 7 plus plus open parentheses 2n minus 1 close parentheses equal n squared minus 1 numbers. So the left side of the equation must start with the number n squared followed by the next n consecutive numbers. N squared plus 1 through n squared plus n. Wow. The right side has n consecutive numbers starting with n squared plus n plus 1. Through n squared plus n 2n. If we temporarily ignore the n squared number on the left, we see that the n numbers on the right are each n larger than their corresponding numbers on the left, so their differences is n times n, which is n squared. But this is compensated for on the left by the initial n squared term, so the equation balance. Wow. Time for a new pattern. We saw that odd numbers could be used to make the squares. Now let's see what happens when we put all the odd numbers in one big triangle as shown on the next page. We see that the 3 plus 5 equal 8, 7 plus 9 plus 11 equal 27, 13 plus 15 plus 17 plus 19 equal to 64. What do the number 1, 8, 27 and 6, 44 have in common? They are perfect cubes. Wow, they are perfect cubes, yeah. 8 is 2 times 2 times 2, 27 is 3 times 3 times 3, 64 is 4 times 4 times 4, right? For example, summing the 5 numbers in the 5th row, we get the 1 equal 1 cubic. 1 cubic. 3 plus 5 equal 8 equal 2 cubic. 7 plus 9 plus 11 equal 27 equal 3 cubic. 13 plus 15 plus 17 plus 19 equal 64 equal 4 cubic. 21 plus 23 plus 25 plus 27 plus 29 equal 125 equal 5 cubic. An odd triangle. Wow. Yoi. 21 plus 23 plus 25 plus 27 plus 29 equal 125 equal 5 times 5 times 5 equal 5 cubic. The pattern seems to suggest that the sum of the numbers in the nth row is n cubic. Will this always be the case, or is it just some odd coincidence? To help us understand this pattern, check out the middle numbers in the rows 1, 3 and 5. What do you see? The perfect square 1, 9 and 25. Rows 2 and 4 don't have middle numbers, but surrounding the middle are the number 3 and 5 with an average of 4 and the numbers 15 and 17 with an average of 16. Let's see how we can exploit this pattern. Look again at the row 5. Notice that we can see that the sum is 5 cubic without actually adding the numbers by noticing that these 5 numbers are symmetrically centered around the number 25, right? It's like a center of gravity, right? Since the average of these 5 numbers is 5 square, then their total must be 5 square plus 5 square plus 5 square plus 5 square plus 5 square equal 5 times 5 square, which is 5 cubic. Wow. Sure. Similarly, the average of the 4 numbers of row 4 is 4 square, so their total must be 4 cubic. with a little bit of algebra, which we want to hear, you can show that the average of the n numbers in row n is n squared, so their total must be n cubic as desired. Wow. Since we are talking about the cubes and squares, I can't resist showing you one more pattern. What total do you get as you add the cubes of the numbers starting with 1 cubic? 1 cube. 1 cube equal 1 equal 1 square. Wow. 1 cube plus 2 cube equal 9 equal 3 square. Wow. 1 cube plus 2 cube plus 3 cube equal 36 equal 6 square. Wow. 1 cube plus 2 cube plus 3 cube plus 4 cube equal 100 equal 10 square. 1 cube plus 2 cube plus 3 cube plus 4 cube plus 5 cube equal 2 to 25 equal 15 square. The sum of the cubes is always a perfect square. Phew, so cool. When we start the summing cubes, we get the total 1, 9, 36, 120, 225 and so on, which are all perfect squares. But they are not just any perfect squares, they are the squares of 1, 3, 6, 10, 15 and so on, which are all triangular numbers. Earlier we saw that these were the sum of integers, and so, for example, 1 cube plus 2 cube plus 3 cube plus 4 cube plus 5 cube equal 225 equal 15 square equal open parentheses 1 equal open parentheses 1 plus 2 plus 3 plus 4 plus 5 close parentheses square. To put it another way, the sum of the cubes of the first n numbers is the square of the sum of the first n numbers. We are not quite ready to prove that result now, but we will see 2 proofs of this in chapter 6. Sure. Alright.